All right, everybody, welcome to my channel. Today I wanted to do a quick video on Hot Standby Routing Protocol, HSRP. It's a pretty important protocol, Cisco proprietary, so if you're an engineer in a Cisco shop, I'm sure you've heard of this or run into this before or implemented it before or did some troubleshooting with it. So it's pretty popular, it's pretty useful, and it's pretty easy to set up. So I'm going to go over just a broad abstract overview of what it is, how it works, and then we'll do some CLI configurations and actually configure it in our topology here. So I'm kind of doing this as a refresher course just for my own benefit, and I figured as I was creating this lab to just share it with everybody else. Hopefully you find it useful, or maybe you get a certain, a little small aspect of it that's useful to you. So that's my hope at least, and let's dive into it. So HSRP, in my opinion, it kind of boils down to the adage or the saying, one is none, two is one. And that has to deal with a single point of failure in your network. So if you have one router in your network that everything else relies on to route traffic through, it's going to fail eventually, just inevitably. Just it's going to fail. Some fault's going to be introduced into it, and it's going to probably happen at the worst time for you. So if you have a backup router configured to take over when that happens, then you still have one router still passing traffic, and business continues to flow through it, and traffic continues to flow through it. So that is the basic idea behind it. Now, the hot standby portion, those two terms, hot standby means this router is ready to take over in an instant. You don't have to do any configuration. You don't have to flip any switches, so to speak, or toggle anything. It's just sitting there ready to take over. And that's very helpful in case something breaks in the middle of the night. You don't have to have an engineer manually fail something over. It just takes over. So that is what HSRP is, and that's really why it's so important and so widespread, because it's just provides redundancy, provides resiliency, and everybody wants that in their network. Now, the technical aspect of how it works is two routers will form a standby group. So their physical interfaces here. In my diagram, I have these two routers. These are going to form my standby group. And we are going to say that these two routers with these two physical interfaces, 10.10.10.1 on router 1, 10.10.10.2 on router 2, are going to form a standby group, and the virtual IP address that they're going to share is 10.10.10.100. So this means that these two routers, they're going to form an election. They're going to say, okay, who's going to be the active router, who's going to take ownership of this 10.10.10.100, and who's going to be the standby one. That's determined by the priority and something called preemption. So by default, the priority is 100. So we have to tweak these priorities to determine which router we want to be the active router. Now, if it blows up or if its priority ever decrements for some reason, as we'll go into later, it's going to communicate with router 2. Basically, they're always in communication. They're going to say, hey, router 1's going to say, hey, my priority just went down. And router 2 is going to be, okay, got it. I'm going to take over as the active router now. So that's the gist of how these routers determine who's going to be the active one and who's going to be the standby one. So this is not load balancing, right? 10.10.10.100 only exists and only responds on one of these routers at a time. So there's a virtual IP address and an accompanying virtual MAC address that's created. So only one router is active or passing traffic at a time. This is not load balancing. So I just wanted to reiterate that. So that's basically the overall idea of what it is and technically how it works. This communication happens over 224.0.0.2, UDP 1985. In case you throw a firewall in the mix and some weirdness happens, you got to make sure that port is open and all that good stuff. So let me go over this topology now. This is the simplest topology I can think of to explain this protocol. I have a Linux PC here. It's operating under DHCP, or it's getting its network parameters from DHCP. I have a layer 2 switch here, and I have these sub interfaces configured on these routers. It's very similar to router on a stick, if you've ever heard of that terminology before. And then I have this section of the network, which is going to act as my ISP. I have two ISPs. I'm going to say this one's, say, Comcast, and then this one is Spectrum or Lumen or whatever other ISP you want to hitch your wagon to. And then 8.8.8.8 is a loopback I created. It's going to serve as our internet reachability, so to speak. Over here I have my commands that I'm going to run. As you can see, they're very simple and straightforward. We're going to go into the sub interface, this one on the router 1. We're going to define the standby group, create the virtual IP address, set its priority 105. It's higher than router 2, which is going to be 99, which means router 1 is going to be the active router. And then I'm going to say preempt. Preempt is short for preemption, and it means router 1 is going to, for instance, if router 1 blows up, router 2 is going to take over. Okay? If router 1 comes back online and everything's squared away, gets its life back in order, if preempt is not enabled, which it's not by default, then router 1 is just going to let router 2 do its thing until router 2 dies, which is not what we want. We want router 1 to come back online and say, hey, I'm back online, I have a higher priority, I'm taking over. So it's going to force a new election and it's going to take back over as the active router. In my opinion, you should enable preemption on your network because it leads to greater predictability, more stability within your network. You're always going to know that if router 1's online and okay, it's going to be the active router, right? So preempt should be enabled. And then we're going to track. So we're going to track this connection right here. We're going to say as long as router 1 can reach the internet, keep its priority high. If for some reason it can't reach the internet anymore, this link is severed, whatever's happening, it can't reach 8.8.8.8, there's a problem on Comcast network, whatever, then decrement its priority, force a new election, router 2 will take over ownership of the 10.10.10.100, and this box will now traverse through router 2 to reach the internet. And hopefully router 2 and this ISP isn't having the same problem. So that's the basic gist of how the track statement is going to play nicely with HSRP. So with that being said, let's get into the CLI and do some configuration. First, we're going to go into router 1. Let's get out of that. Let's do a show IP in brief, just to get the lay of the land. Okay, we're going to go into 10, and we're going to do, so this is the physical interface, the physical sub interface, and we're going to tell it to participate in HSRP and standby group. We're going to create a group 1, and we're going to say the IP that we're going to create, the virtual IP address is going to be 10.10.10.100. Okay, and then we're going to say standby group again, and we're going to give it a priority of 105, which is 5 higher than the default being 100. We have one more command to do before we get out of here, standby 1, preempt, which again is going to say once he comes back online, if his priority is higher, he's going to be the active router again. So preempt. Now, we need to do something else that's not necessarily HSRP related, but it's going to help prove our point for the redundancy for HSRP, and that is we're going to create a track statement to track the reachability from this interface to 8.8.8.8. So let's go in here and do that real quick. IP SLA 1, it's going to be an ICMP echo 1 on that address, and the source interface is going to be gigabit Ethernet 00. Okay, so that's good. And we're going to configure a few more parameters here just to kind of give it a little bit more detail, and then we're going to create a schedule for it. Schedule, we're going to say, let's see here, 1, and then the start time, we're going to say the life, we want this to be forever, and we want the start time to be now, and then we want a track on it, track 1, IP SLA 1, and we want to track the reachability of it. Alright, so that's that. Now let's survey what we did real quick. show standby brief. The interface is the physical interface. The sub interface 0.1.10. Its group is the one that we created, group 1. It's priority 105. Preempt, yes, preempt is enabled. The state, it's active. What's the active one? This one, the local one. Kind of redundant, but and the standby is unknown because we haven't configured it. The virtual IP is 10.10.10.100. Now, while we're at this virtual IP, I want to show you the DHCP configuration that we have. You can have this DHCP server on any device. It could be a Windows server, it could be a switch, etc. For this instance, I have it on the router just to show. So this is going to be the information that my Linux client receives. I'm going to give it whatever the 10.10.10.0/24 network, and then I'm going to give it the default router of 10.10.10.100, which is the virtual IP of the HSRP group. If I gave it the IP of a physical interface, such as this 10.10.10.1, this HSRP, it would defeat the purpose of HSRP. Basically, we'd still be relying on that physical interface. It would go down, and we wouldn't be able to reach anything. So we want to make sure that the default router that we're defining in our DHCP parameters is the 10.10.10.100 or your virtual HSRP IP. So with that being said, I believe I need to configure one more thing in order for this to work. I need to go back into my sub interface here, and I need to track that statement. So track my reachability, my of 8.8.8.8, and if it goes down, decrement my own priority. I'm going to say by 10. So it's going to go from 95 or 105 to 95. Okay, I think that should be good. So that's router 1. Now, let's go over to router 2. Very similar commands that we're going to run on router 2. If it responds. Okay. Let's close it out and try it again. Alright, cool. Show IP int brief. So this one is a different interface, but let's go in here, 02.10. And I need to specify this. Sometimes you type too fast, you get ahead of yourself. Even tab to complete can't keep up with you. Okay, gigabit Ethernet 02.10. So this is my sub interface on router 2. I'm going to do the same thing. Standby, the same group, IP, the same IP. So that command is the same. However, I'm going to do this priority. I'm going to say 99, one less than the default, and I'm going to say preempt, ambiguous command, yeah, preempt, and then standby 1, track 1. I have a similar track statement configured on router 2. I just didn't show it because it's unnecessary. So we're tracking 8.8.8.8, and now you can see in this console log here, this router 2 went from speak to standby because it has realized that its priority is lower than router 1. So we can verify that real quick instead of me just telling you. As you can see, this is the sub interface here. Same group, group 1. Its priority is 99. Preempt, yes. Its current state is standby. The active one is the physical interface of router 1. The standby is itself, and the virtual IP is the same, 10.10.10.100. Now, let's make a test here. So this is our Linux server or desktop, doesn't matter. It's just some client that received the DHCP configuration and has a default gateway of 10.10.10.100. So right now it's pinging 8.8.8.8, which is serving as our internet. And its traffic is flowing right now through the switch, through router 1 to the internet and back. If I shut down this interface, gig 00 on router 1, that will essentially serve as introducing a fault into this provider network, which would mean router 1 can no longer reach 8.8.8.8. That track statement that we configured earlier is going to go down, and the router will then decrement its HSRP priority by 10, which means it will have a 95, which means it will have a 95, and router 2 will then have a 99 still, and it will assume active ownership of this 10.10.10.100. This client will then its traffic will then traverse the switch, go through router 2, and then reach the internet and come back. The client will be unaware. It might miss a few pings, but it will be blissfully unaware of the change that happened. It will just know that it's still reaching the internet. It's still hitting this default gateway of 10.10.10.100. It doesn't know that a different router, different hardware is handling that. So that's what we're going to verify. So we're going to keep this constant ping going. We're going to go into here. We're going to shut that interface down, that outside facing interface. We should see a bunch of nasty things happen. Stuff that you don't want to see on a normal production network. And as you can see, the track statement went down and the HSRP state went from active to speak. It's trying to figure out who's the boss now, right? It kind of knows that it's not the boss anymore. So it's trying to figure that out, and it's figured it out. I'm standby now, so let's see. Standby brief. Yep, its priority is now 95. It was 105. And the active one is 10.10.10.2, which is the router 2. And at standby, it's itself. Router 2, it went to active, as you can see. And we confirm that with our command. Let's make sure this host can still reach 8.8.8.8. It did. We probably missed a few pings up here. Yeah, a little bit. But it's still able to reach the internet now. So let's test the preemption, and then we'll get out of here. We'll do a no shutdown on the interface. We'll make everything come back up. And it'll just be the opposite of what we did. The track statement's going to go from down to up, which means the priority is no longer going to be decremented. This router is going to get its original priority back, which was 105, which means it's higher than 99 on router 2, and it's going to take back over ownership, and everything's going to be back to the way it was. So hopefully that is the case. We see BGP alerts, we see the track statement, and then we see the HSRP statement. So let's just do a validation, and that is true. It doesn't know who the standby is right there. That was kind of strange, but now it did. Everything's kind of settled out, and we're back to the original state. This host can reach 8.8.8.8 again. So there you have it. That's a simple HSRP configuration and real-world application. I know it's not lost on me that I'm doing redundancy protocol, but I have a single point of failure on this switch here, but that's just the way it goes. Like I said, I hope you learned something from it, and let me know in the comments if you have any questions or anything like that. So I'll see you on the next one. Thanks.